Hello, welcome you all. In the today's session, we will solve one of the numerical problem on shaft. Okay, let us take a numerical problem. Okay, in this problem, it is a stepped shaft. One end it is fixed and it is subjected to two torsional moments at this point and this point. As there are two diameters, let us consider the first dimension with 40 mm diameter as the element 1 and this 10 mm diameter it is element 2. So for two elements the number of nodes are 1, 2 and 3. We already derived stiffness matrix for the shaft element. It is Gj by L 1 minus 1 minus 1 1. It is a 2 by 2 matrix where G is modulus of rigidity, J is polar moment of inertia and length L is the length of the element. Okay, now we have two elements, element 1, element 2. Let us find the stiffness matrix of the element 1 and element 2. In this problem it is asked to find the angle of shaft, that is the nodal displacement at node 1, 2 and 3. Okay, let us find the stiffness matrix 1. K1 is equal to, what is the modulus of rigidity? It is 80 gigapascal. As the dimensions are given in millimeters, let us take in Newton per millimeter square or megapascal, that is 80 into 10 raised to 3 Newton per millimeter, 80 into 10 raised to 3. What is J? Pi by 32, it is a circular cross section of 40 mm diameter, pi by 32 into 40 raised to 4 divided by length of the shaft. Length is, it is 8 meters, so 8000 millimeters. 1 minus 1 minus 1 1. Similarly, the stiffness matrix K2 is taken here. This is G value, this is J, pi by 32 d2 raised to 4, that is 10 mm into 10 raised to 4 divided by length of the shaft, that is 4 meters. 4 meters it is 4000 millimeters. In the both equations, in the common terms are 80 into 10 raised to 3 pi by 32. Okay, so 80 into 10 raised to 3 pi by 32 it is taken outside, so remaining values it is multiplied to all the inner elements. 40 raised to 4 divided by 8000, it is 320. It is multiplied to all the elements, so 80 into 10 raised to 3 into pi by 32, it is same for these two values, common values, so it is taken out and the remaining elements it is multiplied to the inner elements of the matrix. Similarly here 10 raised to 4 divided by 4000, that is 2.5, it is multiplied to all the inner elements. So the K2 matrix it is 2.5 minus 2.5 minus 2.5 plus 2.5. Now we have two matrix, stiffness matrix. Okay, the assembly of the two matrix, adding K1 plus K2, now we have the 3 by 3 size of the matrix. 320 minus 320, it takes first row first column, first row second column, first row first column, first row second column. Similarly this minus 320, this 320, second row first column, second row second column, minus 320 plus 320, second row first column, second row second column. Similarly this K2 matrix, it is of second node and third node, it is so it is second row second column, second row third column, second row second column, second row third column. There are two elements in the second row second, so it should be added. Okay, so now we have this global stiffness matrix. We already know the equilibrium equation, that is KQ is equal to F, where K is the global stiffness matrix, this is the global stiffness matrix. It is the common term taken outside for both the matrices, both the stiffness matrices 7, 8, 5, 4, 3. So it should be taken out. Next, Q is the nodal displacement 0. It is unknown values, unknown angle of twist at node 2, node 3. As node 1 it is fixed, it is taken 0. And force vector, there is no moment or torsion moment at node 1, so it is 0. There is no torsion moment. At node 2, 90 kilonewton meter, it is converted to Newton millimeters, so 90 into 10 raised to 6, 90 into 10 raised to 6. and similarly the force or the moment at node 3 it is 100 into 10 raised to 6. Okay, so there is no moment or force at node 1, it is 0. At node 2 moment it is 90 into 10 raised to 6, and node 3 it is 100 into 10 raised to 6. So by elimination approach method, we know the nodal displacement, that is angle of twist at node 1. It is a known value, it is 0. By elimination approach method, as we know the nodal displacement at node 1, that is angle of twist at node 1, it is 0. So the first row and first column can be eliminated. So now we have, it is reduced to 2 by 2 matrix. Solving this, we get the angle of twist at node 2 and node 3, it is 75.59 and 5168.55. It is the angle of twist at node 2, node 3. You can solve it in the calculator by the matrix mode or the equation mode. I solved this problem in the Excel sheet. Okay, you can see this one. Okay, this is the global stiffness matrix after eliminating first row and first column. 322.5, 322.5, minus 2.5, minus 2.5, plus 2.5. Okay, the same elements are taken here, and it is the common term. It is the common term. It is the common term. Okay, see, when it is multiplied to all these elements, we have these values. We know that equilibrium equation kq is equal to f. To find this q, that is nodal displacement, that is phi 1, phi 2, phi 3, q is equal to, if k comes this side, it is k inverse into f. So inverse of the matrix, inverse of the stiffness matrix, this is stiffness matrix, inverse value are calculated here, and force vector, this is the force vector, 90 into 10 raised to 6 and 100 into 10 raised to 6. Okay, when the inverse of the stiffness matrix and force vectors are multiplied, then you will get nodal displacement, that is phi 2 and phi 3. Okay, which are same, it is 75.59, 5168.55. It is just for a reference. Okay, you solve it in your calculator, either you solve it by in the matrix mode or you consider it as a simultaneous equation. Okay, thank you.